An angry rhino with a mass of 2,700 kilograms charges at you with a speed of 4.2 meters per second. Before you start running, you try to throw a ball at the rhino. It's a 0.18 kilogram ball and got a 6.58 meters per second speed. Can you determine the speed of the ball that would bounce back after it collides with the rhino? Alright, so let me just draw the situation here. We have two objects in question. I'm going to call them Object 1 and Object 2. Now, M1 is quite a bit larger in mass than M2. That's an understatement. And we're going to see what the results of that are going to be, after they collide. How does that play a part in the changes in velocity that they experience? We all know a rubber ball is not going to do much to stop a charging rhino, and the equations should reveal that, So we're going to have a M1 and a V1. So V1 for the rhino is 4.2, and our V2 for our ball is 6.58. However, in these types of questions, you have to take into account the directions of the velocities. So, with that in mind, one thing I might do is attach a negative to one of them. So I'll call this one 4.2i, so he's going to the right, whereas this guy can be negative 6.58i, showing that he's going to the left. That's going to be important in the calculations. All right, what we need in collisions is we need conservation of momentum. You always want to start with that, because all collisions in the universe are going to obey this principle of conservation of momentum. Sometimes there's conservation of kinetic energy, but sometimes there's not. But there's always conservation of momentum. So you just my advice is, with any of these problems, just start with that. And sometimes that's all you need to solve the problem. Sometimes, though, we need more in order to solve the problem. So since we're going to have conservation of momentum, we're going to have to say that the sum of the momentum before has to equal the sum of momentum after. And we saw last time that momentum has a formula. P equals mv was the formula. However, momentum is a vector, meaning the direction is important. So now when we add up all the momentum, we have to add up initial momentum of the rhino plus the initial momentum of the ball, and then set that equal to the final momentum of the rhino plus the final momentum of the ball. You need 4 terms typically when you're having two objects interact. So these are obviously the before quantities, and these are the after. Then what I'm going to do is I'm going to substitute in a formula for P. It's going to look like this. Now I'll just plug in the relevant quantities. So we certainly know the rhino's mass and his velocity. We certainly know the ball's mass and velocity too, so we can have everything we need for this left side. A problem here is we don't have just one variable that's unknown. We're actually going to have two unknowns. So what that means is that we're not going to be able to solve this problem with just one equation. As you can see, the Rhino has a ton of momentum. Got a lot of mass, moving at a high speed, but the ball has hardly any. That's significant when it comes to the result of this collision, right? So let's subtract here. The sum of their momentum is 11,339 in the forward direction, and that has to be conserved. Okay, this type of collision they mentioned was elastic. When you have an elastic collision, you're going to have conservation of kinetic energy too. So you need to make another equation. Alright, so we need the sum of the initial kinetic energy to equal the sum of the final kinetic energy. So we're going to have our K of our Rhino plus our K of our ball initially. That has to equal the K of the Rhino and ball at the end. We have a formula for kinetic energy that we can substitute in here. Formula was that it was going to be 1/2 mv squared. So let's now substitute that formula in for every term here. And we have that. Now what I'll do is I'm going to plug in the information just like before. So I'm going to know how much kinetic energy there was at the beginning. And what this is going to give us is 2 equations and 2 unknowns, which is technically solvable in math. Alright, so let's calculate how much energy we had. I get a total of 23,818 joules, I believe. Rhino contributes 23,814 joules. The ball contributes only 3.897 joules. And now with these, I'm just gonna simplify the numbers. We'll get 1350 V1F squared plus 0.09 V2F squared. Okay, so now that we have that all plugged in, we have to solve this system of equations. This equation and this equation together needs to be solved. Now you could certainly do it by hand, but since I want to get my answer fast, I'm going to use an online equation solver. Now you may want to rewrite your equations when you plug it into the solver. So I'm going to change the final speed of the Rhino into a letter such as X, and then I will change the speed of the ball into Y, because it's going to be easier to plug in that way into the solver. Okay, so that's one of the equations. This is the momentum equation. And then we have our energy equation. So alright, so now let's go to an app such as Desmos. So in Desmos, type in your equations. Okay, now you just have to know how to interpret the answer. So you're going to have to look for where the functions intersect. Now, you're going to have to scale your view a little bit to see it. So let's change the x-axis so we can see better. One of them is an ellipse, The other one is just a line. But we're going to have to find where they intersect in order to get the answer to the system of equations, right? So if you click on this point, it's going to lock on to the solution. So if you just click where that gray dot is, that is one of the solutions. And there is another solution. So two places where they're actually intersecting. If I change the scale a little bit more, maybe we can see that even better. Yeah, so if you really zoom in, you can see the intersection of the two curves. So one of them is going to actually be your initial conditions. At one point in time, before the collision happened, the Rhino had been running at 4.2 meters per second. That is this lower solution here. It says that one possible solution is that x is 4.2. That's the Rhino's velocity. And then the ball's velocity is the 6.23. You don't want that solution, of course. We want the solution that's after the collision. And what this shows is that Rhino's velocity hardly changes at all. He was going 4.2 meters per second. Now he's going 4.199 meters per second. So the ball didn't really have an effect on him. However, the ball experiences the greatest change in velocity in this collision. He's now going 14.6 meters per second, and now it's positive where he used to be traveling in the negative direction. So it really rebounded at a great acceleration and a great speed there. But that is going to be our final answer, 4.199 and 14.6. Let's write that in. I'll redraw it after the collision. Okay, so there's our V final, 4.199, and our V final for the ball, 14.63. It's important to note that both of these objects feel the same forces when they collide. That goes against intuition. Okay, we all know the Rhino is scary and big and massive and can easily destroy a ball. But that doesn't mean that the Rhino pushes harder on the ball than the ball pushes on the Rhino. That's very counterintuitive of a concept. Okay, but by Newton's third law, we showed in the past that it's true that they exert the same forces on each other. Otherwise, Newton's third law would not be obeyed. The force of 2 on 1 has to equal the force of 1 on 2, but they are opposite in direction, equal in magnitude. But the reason why the ball experiences such a change in its velocity is because of Newton's second law. Okay, he will experience an acceleration that is equal to the net force that he feels divided by his mass. Okay, whereas the Rhino feels an acceleration equal to F net over his mass. Now you know that the Rhino has a huge mass. Okay, this is huge for the Rhino. For the ball, it's tiny. So even though they have the same net force that they feel, the accelerations are that this Rhino will have hardly any acceleration. For A2, it's a huge acceleration.